Hey, Precalc, welcome to paradise. There's a pair of dice, and here's our do now. Please copy and complete the expansion, that multiplication box there below. Hit pause while you get that thing filled in and written down. You'll definitely need a written copy of that later. I'll hang out till you're done. Yep, all right. Well, I see that you finished your table. I finished mine. So I got an extra question. Now that we have the table completed, how many different rolls would award you a sum of 5? So we take a look at that table, and a sum of 5 would show up here. We got the 4 on one die. We got the 1 on the other die. They show up also here and here and here, which is a total of 4 outcomes. Give you a sum of 5 when you roll 2 dice. So today, we would welcome you to Fish Tactics. Today we're going to look at polynomial modeling. And learning target remains unchanged. You'll be able to use counting methods to find outcomes. The counting method we're looking at in particular today is polynomial modeling. And this is something we've been building towards the last several days. Since we've actually done some of it, but this is the entire focus of today. So, for example, a couple of days ago, I gave you this do now, which involves 2 wheels of fish, 1 fish, 2 fish, red fish, blue fish on the one spinner, and then the all green on the other. And I asked you to make a table. I showed you a double axis table. We put the outcomes of one fish, wheel of fish on one edge of the table and the other spinner on the other edge, added them all together. So there's some similarities and some differences between this table and the one you just made in the do now. The important difference is this table was a table of addition. So we put the numbers on from one wheel of fish on one edge, added them together with the numbers from the other wheel of fish to get our sum in the body of the table. And the table you just made in the do now was multiplication, because we were modeling this expression here, x plus x squared plus x to the power third, x to the power fourth plus x to the power fifth, x to the power fifth. That expression to the power of 2, which means multiplied by itself. The thing is, when you multiply an expression by another expression, if the variables have exponents, we end up adding the exponents together. And so the outcome appeared very similar. We just added the exponents from the top row with the exponents on the side, and we ended up with a pretty similar outcome to what we saw in this table from last week. Okay, another way we've been leading up to polynomial modeling is we modeled coin flips by using an algebra expression, a polynomial. So tails and heads both represented the 2 outcomes on a coin. If we did 1 coin flip, there's not actually any multiplication to get our expansion. When we did 2 coin flips, we had to use a multiplication box, which is not shown here. And then we could take this answer and multiply it by h plus t again. With a larger multiplication box, we got our next answer. And then we could take this result and multiply it by h plus t yet another time, and an even larger multiplication box to get the next outcome. And so each of these represents the actual sample space. All of the outcomes possible, the different combinations of the coins, if you were to flip a coin 3 times, or if you were to flip a coin 4 times. So the expression there, the coefficient tells us the frequency. There's 1 possible way to get heads on all 4 coins. There are 4 outcomes to get heads on 3 of the coins and tails on 1 of the coins, and so on. So the coefficient is telling us the frequency, and then the variables and exponents are telling us the specifics of the outcome, which is essentially what we use a polynomial model to do. So this polynomial model, we didn't know it by that name, had different outcomes. We assigned them different variables, an H for heads and a T for tails. And so today we're going to look at numerical outcomes like you saw in the do now. So quick review to help us understand where this is coming from. We saw earlier to calculate the size of the sample space, we can do an exponent formula where the base is the number of outcomes for one individual trial. So if we're flipping a coin, it's got two sides, and so we'd use 2 as the base. And the exponent is the number of repetitions. So if we're doing 3 coin flips, we'd use an exponent of 3. 2 to the power of 3 would give us the size of the sample space. How many outcomes are there, different combinations? We could replace the base, instead of the number of outcomes, we can replace it with the actual outcomes, like H and T, a different variable to represent each of those different outcomes. And then do the algebraic expansion, H plus T multiplied by itself, again and again until we get to the power of 3. And that expression that we come up with describes the sample space. It doesn't tell us how many, it tells us how many things are in it, but it actually gives us all of the outcomes in the sample space. Right, we can see them all described here. There's 1 outcome with heads 3 times, 3 outcomes, heads twice and tails once, and so on. Okay, if we take that one step further, we can use the same approach for numerical outcomes. We can actually get the whole entire sample space by using this kind of polynomial model. So it's an algebraic approach that we can use to find the entire sample space of a repeated event. And it is actually what you just saw in the do now. So if we're rolling 2 dice, we're going to use anything we want for the variable. In this case, the variable doesn't actually represent an outcome. It's the exponents that we're interested in. So with the heads and tails, we distinguish the outcomes with different variables. In this case, on a die, the outcomes have different numbers. And so we just are interested in the different exponents. So we got x to the power 1, x to the power 2, x to the power 3. All of these exponents represent the numbers on the different sides of the die. That's inside the parentheses. That's our base. And then the exponent is still the number of repetitions. So for 2 dice, if we're going to roll the 2 dice and add them together, then this exponent represents how many dice. Okay, when we do that algebraic expansion, like you used the table to do in the do now, the result is all of the sample space. It's all the possible outcomes for that repeated event where we're adding together the repetitions. So whatever number you rolled on one die added together with whatever you rolled on the second die. So each of these terms represents a different outcome or a group of outcomes that give you the same sum. So for example, in that table that we saw from the do now, I asked you how many different sums were there, how many different ways to get a sum of 5. Right, and we see that right here in that blue expansion. There's the coefficient, which I've below there I've highlighted in yellow. That tells us the frequency. There are 4 different ways to get this value. The exponent tells us the sum. There's 4 different ways to get a sum of 5 when you roll your 2 dice. Right, so just like in the picture, you could have a 1 on one die and a 4 on the other. This is one of the possibilities. Or you could switch it around. You could have a 4 on the first die and a 1 on the second die. So that'd be the second one. You could have a 2 and a 3 or a 3 and a 2. Right? So there's 4 different combinations that are going to give us that sum of 5. And you listed those already in the table. Okay, so these are the things we got to keep track of. If we're going to use a polynomial model, we need to know what the different parts of it mean so that we can interpret it and it's actually got some meaning for us. So the coefficient is the frequency. Exponent is the value. Okay, those same descriptions apply when we're creating the polynomial model. There were no the coefficient of 1 is not written on any of these, but there's one side with each of these different numbers. And then the exponent represents the value on that face of the die. So I'm not going to have us go through creating this frequency table, but you can, just as a thought experiment, think about collecting all of the like terms. All the different exponents represent these different values. If we went through that table, we'd want to combine the like terms. We did, as part of the do now, the different ways you could get a sum of 5, and we can see there's 4 of those things. And so this is a different approach. We could kind of do by hand the algebraic expansion. Take our x to the power of 1 plus x to the power of 2, that expression, and put it on 2 edges of a multiplication box, collect the like terms. Okay, and so to do an expansion like that, multiplying by hand is an option, right? So this is a different example. This is kind of the alternative. It's not actually what we're going to use, but just so that we can appreciate the value of the tools, we need to see where this comes from. So if our polynomial were x to the power 7 plus 3 x to the power 4 plus x to the power 0, that thing raised to the power of 3, then we would need to take this base expression and multiply it by itself. So we could use a multiplication box. And that's once, twice. So this multiplication box gives me that expression to the power of 2. So I need to take this red bit here, combine the like terms, simplify that, put that on the edge of another larger multiplication box, multiply by the original expression in green. Again, fill in this whole entire multiplication box in blue, combine like terms, and then that would give me my entire sample space down at the very bottom. So that expression at the very bottom of the screen there, that is the entire sample space for doing 3 repetitions of the event described by that original polynomial model up here at the top of the page. So if we had, this is not really probably a die, it's probably like a spinner or something like that, where you've got a 7 on one side, you've got 3 sides that have a 4, and you got one side that has a 0. If we're going to do that, that spinner or die or whatever it is 3 times and add them together, here are all the possible outcomes. Okay, so that's one option. We could actually multiply this out by hand. And if this was the only option, this is not a thing that we would be studying right now, because that is way, way more work than what we gain. And so it's not as valuable of a tool if we have to do it that way. But we don't have to do it that way because we have technology to assist us. And so instead of multiplying that polynomial by hand using multiplication boxes and larger multiplication boxes, we're going to use a website which contains a polynomial calculator that will do the multiplication for us. We just have to type it in. And that is at wolframalpha.com. And this input bit over here is actually not needed. You can type it, or not type it. It'll take you to the same place. So this is a math website created by Mr. Wolfram, hence the name. And let me get this link open. So if you were to type an expression into the little box, it looks like it's a search engine. It's not actually a search engine. There's just, that's the input box. So we're going to type an expression, a polynomial model, into this box, and it will calculate for us. So let's get an example, and then I'll show you how to type this in here. So let's do this one. Let's set this up first. So I have a spinner, and I've created a polynomial model for this spinner already. So here's the spinner. It's got a 1, a 3, a 3, a 7, and a 0 on it, and you spin whatever number lands on. That's your number. You get 4 spins. This is a wheel of fish. Somehow you won some bonus spins, and you're going to walk away with hopefully a lot of fish. So I've created a polynomial model. One space on the spinner has an outcome of 0. So the coefficient is the frequency. Exponent is the value. One space on the spinner has a value of 1. 2 of the spaces have a value of 3. And so I changed the coefficient because there are 2 spaces. And so that's my frequency. Value of 3. 1 space has a value of 7. So that whole expression I'm going to do to the power of 4 to model 4 spins added together. Okay, before we go any further, let's calculate the size of the sample space. So I don't need that polynomial model. If I'm going to find the size of the sample space, I just need to know the number of outcomes as the base and not have a polynomial to describe the outcomes. So how many spaces are on that wheel of fish? 1, 2, 3, 4, 5. And I'm still doing 4 spins, so 5 to the power of 4, which is some large number, I think 1024. All right, so in order to expand this polynomial model, I have a choice. I could get some multiplication boxes and like reams of scratch paper and do the multiplication myself, or I can type it in here. So I'm going to try to resize this window so that we can see. There we go. Everything at the same time. So I'm going to go ahead and type in this polynomial. The coefficient of 1 is actually not needed. I could leave that off, but I've typed it already. So 1 x to the power of 0 plus 1 x to the power of 1 plus 2 x to the power of 3 plus 1 x to the power of 7. Close the parentheses. That whole thing raised to the power of 4. So make sure when you're typing these things in here, make sure you get the parentheses in the right spot. In the right spot. You need round parentheses. If you use the square ones or the curly ones, it does weird stuff. And make sure you get your exponents into the right spot after the x's, and it's hard to keep track of what's going on there. Sometimes it's easier to see if you space things out. Spaces don't have any effect on the calculation. It just makes it easier to see stuff, so you can see each of the terms a little bit easier. Anyway, once you get that typed in there, just hit enter. And it's going to calculate like every conceivable math thing it could possibly do. Algebra, pre-calculus, calculus, all kinds of stuff you've learned, haven't learned. Someplace in here is the expanded form, the multiplication. So you can see there's a whole bunch of stuff. Here's what the input looks like when it's all typed pretty. And then there's like other ways of writing it, graphs, other kinds of graphs, alternate forms, expanded form, roots, complex roots, graphs in the complex plane, discriminant, properties of real functions, derivatives, integrals, I mean, like there's just like a ton of stuff. And then it would have done more, except my standard computation time was exceeded. So, oh my gosh, there's more. All right, well, the only thing I'm actually interested in is the expanded form right here. And so I already got a copy of the screenshot right there. But maybe you don't want to have to dig through this whole list of math stuff to find the one piece of information we're after, because it does, it doesn't know what you're after. You typed in an expression and it just like did, I can do a bunch of math with that. But if you want to give it some directions, go to before you type in the polynomial model, just type the word expand, and that'll give it some directions. So if I had typed expand and then the same polynomial model, hit enter, now it's going to put that expansion at the top, and so I don't have to search for it, which is nice. And then it still does a bunch of other math afterwards, but I want this expansion. Okay, so here is that expanded form of my polynomial model. So I've got and highlighted in yellow, I've got the original polynomial model, not expanded, and then I've got the multiplied form that actually describes the whole entire sample space. If I ask you the question, what is the most likely number of fish? How would we identify the most likely number of fish? Well, most likely means it's going to happen a lot, right? Happening a lot means it would have a high frequency. Frequency is the word that describes how often something happens. So whatever's got the biggest frequency will be most likely. Where do we find frequency? I wrote down where to find frequency someplace right there. Frequency is described by the coefficient. So we are looking for the largest coefficient in that polynomial model. Largest coefficient in the polynomial model, and that is definitely not this one, which has a coefficient of 1. 8, 4, 4, 24. This is the biggest one so far. And if we keep going through there, 54 is pretty big, but 60 is bigger. So here is the largest frequency. It happens 60 times. But that is not a number of fish. 60 is the number of times it happens. The number of fish is the exponent. The exponent is the value or the sum. You did the 4 spins, you got a sum of 10 fish. So the most likely number of fish is, what am I writing? 10. I don't know why I wrote that. That's a weird number I pulled out of a hat. 10 fish. Next, if I asked you what is the probability, of winning 10 fish, now that we've established that is the most likely outcome, to find probability, I'm going to use not the 10 fish, but the frequency. So we're going to pay attention to wording. If the question says, what's the most likely outcome, we're going to look for the exponent. We find the biggest coefficient, but the number of fish would be the exponent. If the question asks for probability of winning that number of fish, well, probability, I need to make my probability fraction, I need the frequency, which is 60. And also, I'm going to need the total size of the sample space, which was 1,024. It's not 1,024, is it? Size of the sample, let's see, 5 times 5 is 25, 1 5 is just, oh my gosh. You know what? This answer is actually not even the right answer. Let's back up. I'm sorry. Okay, if we actually do math, instead of just trying to work from memory, 5 times 5 is 25. Multiplied by 5 again is 125. Multiplied by 5 again is 625. It's helpful to use correct answers. So our probability fraction would be 60 over 625. And you should always reduce fractions. I mean, that is good mathematical practice, and so this should be reduced. You can divide, let's see, both of those divide by 5. So we could simplify this to 12 over 125. Mental math. That does not reduce anymore. Now let's look at an example, a practice problem. Here is a wheel of fish. Just pictured in the picture there. Please write a polynomial to model 1 spin of this spinner. And also, question 2, write a polynomial model to model 7 spins of this spinner if you're adding all the spins together. Go ahead and pause while you get your answer, and then we'll get, when you're ready, go ahead and hit play, and we'll compare answers. All right, well, hey, welcome back from pause. So here's my polynomial model for 1 spin. I don't actually need parentheses here, but I'm going to use them anyway. So I got 2 spaces that have an 8. So coefficient of 2, exponent of 8. 1 space with a 6, 1 space with a 5, 1 space with a 4. Do you need to go in any particular order? No. I like to go in descending order. It's the math convention. But if you didn't go in order from largest exponent to smallest, no big deal. Sometimes people ask, like, hey, well, did I need to use a coefficient of 2 because there were 2 spaces that had an 8 on them? You did not have to write it that way. I mean, we do need to get both of the spaces that have an 8 in there. You could have just said, look, 1 space has an 8, another space has an 8, another space has a 6, another space has a 5, and another one has a 4. That's actually equivalent. Because if we think about combining like terms, these 2 x to the powers of 8 are going to combine, and there's 1, 2 of them. So I just wrote it 2x to the power of 8. Either way is equivalent. Neither way is wrong. Then question number 2, write a polynomial model for 7 spins. And so I'm going to take the polynomial that I had over there in number 1 and stick an exponent on that whole expression to the power of 7. While you guys were writing down your answers and I was on pause, I got the expansion of that polynomial raised to the power of 7, and here it is. What is the most likely outcome from 7 spins of this wheel of fish? Take a minute and look through there, see if you can identify the most likely outcome. So it is not this one, because I know that is not the largest coefficient. So the largest coefficient I'm seeing is this one, 7,154. Double check, anything bigger than that? There is not. All right. So the coefficient is where is how I identify the most likely outcome, but that is not actually the answer. The outcome is 44 fish, because that's the exponent. Next question, how likely is it that we would win 44 fish? Well, we're going to do a probability fraction. So 44 does not go in my probability fraction. The coefficient goes on the top of my probability fraction. The bottom of my probability fraction is the total size of the sample space. So to find the total size of the sample space, if you're not remembering, I'll give you 2 options. One option, add together every single one of these coefficients in that whole entire expression. Don't forget the 1 right there. Okay, while you guys are adding all of those together, here's option number 2. To find the size of the sample space, exponent is our formula. The base number is the number of outcomes for one trial, so that spinner had how many spaces, and the exponent is the number of repetitions, or spins in this case. So this spinner has 1, 2, 3, 4, 5 spaces, and we're doing 7 spins. So 5 to the power of 7. Size of sample space, 5 to the power of 7, which I imagine is a large number. Let's see. 5 to the power of 7. 78,125. 78,125. All right, well, there's the bottom number of my probability fraction. That's a pretty ridiculous probability fraction, but that is the probability. All right, here's an example out of the assignment, starting from the top. In a strange place called eccentricity, there's a wheel of fish that has the numbers 2, 3, 6, and 11. Write a polynomial model for 5 spins. All right, so I'm going to use those outcomes as my exponents. X to the power of 2 plus x to the power of 3 plus x to the power of 6 plus x to the power of 11. Close those parentheses. Raise that whole expression to the power of 5 spins. And moving on, Jill claims, as a resident of eccentricity, that she was awarded a spin, 5 spins to the wheel of fish. She says she spun 5 times and won a total of 43 fish. Is this unusual? How am I supposed to know if that's unusual? I don't know, Jill. I don't know what happens in eccentricity. It seems like a strange place. Could that happen? I don't know. Well, I need to go to the polynomial model to find out, essentially, is what we need to do. So WALMAP is not going to give you the expansion of this polynomial model. So we'll need to go to Wolfram Alpha to get the expansion of this polynomial model. And then we could have a more informed answer for whether 43 is an unusual number of fish. So I'm going to take this polynomial model and retype it over here in Wolfram Alpha. So this is my previous model. I got to change the exponents 2, 3, 6, and 11. Get rid of that coefficient. Change the number of spins to 5. If you could totally have started from the beginning. So I got 1 space with a 2, 1 space with a 3, 1 space with a 6, 1 space with an 11. 5 spins. Still got my directions of expand. Just going to do some quick check, 2, 3, 6, and 11. Make sure I got the right thing remembered. Okay, so I'm going to hit enter again, so we'll actually calculate what I just typed in there. All right, and here is my expansion. So the question was about 43 fish. Is 43 fish unusual? All right, I'm done zooming. You guys see 43 in here? I don't see 43 in here. 43 is not in here. You can see, starting from the highest exponent, 46, 45, skips to 42. What does that even mean? It means 43 is not a possible number of fish you can win. If you got 5 spins on this spinner, there is not a way to add the numbers on the spinner and get an answer of 43. It's not possible. If it were possible, it would show up in our list. So, get back to the right screen. Jill claims she won 43 fish. Is this unusual? Yes, it's unusual. It's not even possible. Jill is a liar or has a bad memory. But you can't win 43 fish. So is it unusual? Yeah, it is. Later, we'll learn some ways to determine if something is actually possible. Would we still deem it unusual or not? At this point, if it's not possible, we have to say it's unusual. It can't happen. The size of the sample space is how big? Well, either add all of the coefficients in this expanded polynomial model, or you could do it the faster way. Just keep going back to the same screen so we keep remembering number of outcomes on one trial as the base, and our exponent is a number of repetitions. So this spinner has 1, 2, 3, 4 spaces, 5 spins, 4 to the power of 5. I do this correctly this time, 625. Frequency of winning 23 fish. Oh, 23 fish. I don't know. Let's find out. 23 fish. 23 fish is right here. 23, the number of fish, is the exponent. I need the coefficient to get the frequency. There are 45 different combinations of spins that would give me 23 fish. That's the 45 that I'm after. 45. Probability of winning 23 fish as a probability fraction. So 45 on the top, 625 on the bottom. Apparently cannot do good math. 4 to the power of 4 to the power of 5. I thought I was going to do better this time. That's okay. We'll get it right the second time. All right, so 4 to the power of 5, 1024. Maybe you should actually use a calculator instead of trying to remember random numbers like I'm doing. Probably will work better to use the calculator.